This is video 25 in the series of concrete slabs. We will talk about strut and tie models. A strut and tie model, it's typically used in retaining walls. It's used for double corbel beams. It is used for the corbels and also for the pre-stressed to introduce the pre-stress into beams. There are a few examples where you have to use strut and tie models. Some general remarks regarding struts and ties. When you have two struts diverging, then this leads to a tension tie on the bottom of the two struts. When they are converging, then it leads to compression. That's a general principle. For a deep beam, for instance, when there are two local loads, then the local load is introduced for a short distance straightforward down, then they will diverge, and at the end you will have a tie, and on top, when the compression struts are converging, you have also a compression strut. You can, for a beam, for instance, you can have a strut and tie model, and then which is well known, for instance, for shear force, and then you know that this is the strut elements, and then the green ones are the ties in tension. Let's look at the example of a deep beam support of a bridge, which is supported by, for instance, three piles of foundation, and this is the concrete. When you have four points where the beams of the bridge are supported, then you can draw the strut and tie model. At the left and right side, then the load is directly carried over to the nearest point of support, left and right. The other load, it will look for the nearest point of support, so it will be to the right and to the left. So that's also a compression strut, so no problem with that. The same happened with the other load. It looks for the nearest support, and then you have another strut. Now we will look for the ties. Now, obvious, when you have here two struts fanning out, so this will be a tension tie. What about the top? Well, this is fanning out, so this is tension 2, tension 2. And what about the middle one? The middle one is an exception because this is not a tie but a strut. And this is because this strut and this strut, it's shrinking due to the load. It will shrink a little bit, but it will shrink, and this will shrink. So the total length of the strut in the middle shortens. This means that there is compression. Why is this not the case? Because this is shrinking and this is shrinking. So why is this not a compression? Well, this is not hindered. So this can go to the left. So that's why this is tension, to prevent it, this point going to the left and this point going to the right. Let's take now as an example a beam with two corbels. These are the 2 point loads coming from the floor or from other beams. You see immediately that there should be a strut like that going to the direction of the main body of the beam, the same to the other side. Those two, it's two struts fanning in. So it means that there is also a compression strut. On top, it's a tie. but it's not all, because now you have to tie this in with the main body of the beam. And now you can calculate the tension in the ties and the compression in the struts, and you can calculate the needed reinforcement. You can have other models. This is, for instance, a model where there is a concentrated load on a column, for instance, or a concentrated load introduced by pre-tensioning or post-tensioning. And then you will see that this load will first fan out. You have somewhere in a certain depth, Z, you will have a tie with tension, and then you have compression again, making equilibrium with the reaction force. So for anchor block, pre-stressing anchor block, there's a tie reinforcement, and for columns, there's also a confinement reinforcement needed to take up the tension, which is, just take care, which is perpendicular to the load itself. Let's do some estimations of how big are those forces. Let's suppose that the angle of the compression strut is theta. And you have a block of concrete with dimension A, and the tie is of the center width of the tie is situated at a level beta A. In this case, we see on the top that when this is the hook theta, and then this is also the hook theta, and then this dimension is 1 min beta times A, because this is beta A. Then you can see that the tangents of the theta is equal to this expression. A1 is the width of the support. And then the tension force in the tie is P over 2, total load divided by 2, divided by tangents theta, and tangents theta is this, so we have this type of formula. Beta now is situated between 0.5 and 0.6 times the height A. So that means that the tension force F1 is between this value and this value, or in practice, very practical, we say that the tension force is more or less 1/3 of the total load multiplied by this geometrical factor. A foundation block, for instance, with a column and with two foundation piles, then you have a strut directly to the piles and a tie to keep those struts in place. Another example is when when you have to take care of confinement reinforcement at concentrated loads. You should think that when this is a concentrated load and then this is also a concentrated load, that this is fine, and that there is no tension at all, which is not the case, not at all, because you have always fanning out the compression struts and the other side too, and then they make somewhere in the middle an equilibrium, and because of they are fanning out, you have tension ties. You have ties there on a level like 0.3 times the total height of the block. So don't forget this. This gives cause to a lot of crack widths in concrete blocks. Now we look at a deep beam. For instance, it can be a wall of an elevator, and this can be the load coming from the floors. And the wall of the elevator is supported by, for instance, two foundation piles. This load is then concentrated into two locations in struts, and those struts are directed versus the foundation piles. We know that the top then is compression strut and the bottom is a tension strut. The level Z where where this N2 is situated, where the point of gravity of N2 is situated, is in fact a little bit unknown, but by experiment we see that depending on the proportion length divided by the height of the deep beam, Z equals 0.6 L, or for other intermediate values, it's a combination of H and L. In practice, we use Z is equal to 0.6 L. The center width of the tie is situated at 0.075 times the minimum value of H and L. We take the same type of wall and are going to calculate some or going to develop some formulas. You have a wall loaded by a uniform distributed load Q. We assume at this stage that the proper weight of the wall is neglected regarding Q, or you can put Q inclusive of the permanent load of the wall. But it will not appearing in this formula. Let's say Q is inclusive the permanent load of the wall. Distance between the support is L, and the width of the support is A. So the total width of the wall is B equals L plus A, and the height is H. Now the total load is then equal to Q, which is the load, times the width of the wall divided by 2, because we look at the load coming into this compression strut. This is the hook theta that the strut is making with the tie, and then you can easily see that the tangents of this angle is Z divided by B over 4 minus A over 2. The tension in the tie is, like we have seen before, P divided by the tangents of the theta, and the reinforcement is just the tension T divided by the yield stress of the reinforcement. And the compression in the strut N1 is then P divided by sinus theta, N2 is N1 times cosinus theta, this is N2. And when we have all those forces and reinforcement, then we have to check the nodes, and you have 3 points of checking. It's level 1, which is just on top of the pile, then section 2, which is just on the bottom of the first strut, and section 3 is within the strut. And you see that to fulfill all requirements, then P over AB must be smaller than 0.85 nu FCD, N1 divided by this surface must then be smaller also than 0.85 nu FCD, because P equals N1 times sinus theta, and N1 divided by the cross section of the strut must be smaller than 0.6 nu FCD. So you have 3 checks, and those 3 checks allow you to design the deep beam. Let's have a small summary for deep beams, because you have different situations. We should not confuse them. A classical deep beam on 2 supports uniform distributed load has this shape, with the situation of Z equals 0.6 L, when in the case that L is smaller than H, of course. So 0.6 L. The second case is when there is no point support but a continuous support, and you have one load and is brought back to the continuous support, then you have this type of strut and tie model with the situation of this strut of this tie, with the situation of this tie at a level of 0.5 L. And then the third situation is when you have 2 loads diametrical to each other, then you have the situation where the tie is situated at 0.3 h.